So far we looked at one case where an object was speeding up over a distance and the velocity increased at a constant rate, and that was it. Now, what if our velocities change? So maybe the object speeds up and then reaches a cruising speed. That would look like speeding up and then a cruising speed. So an example would be if you are at a stop sign in a car and then you take off, and so you start from rest and you speed up to some final velocity, and then you maintain that velocity in the car. So this shows me two steps of the motion. Now, this section here has a positive slope because it's up and to the right. And so the acceleration in this section is positive. The acceleration in this section would be 0 because the velocity is remaining constant. So velocity is a constant for this section. But this interval, the velocity is increasing. So while velocity gives us magnitude, which is the number, and direction, which tells me left or right, I have to take that into account because not everything moves in the positive direction. This graph shows me that an object starts from rest, speeds up because these numbers are getting bigger and bigger as we go away from the axis, and then maintains a constant velocity here. Now, it's important to remember that the sign represents the direction. You can't go slower than stopped. So a -2 meters per second means you're moving 2 meters per second in the opposite direction. So over here, we were moving in the positive direction, and so our positive acceleration gave us an increase in our velocity. Now this slope here is negative. So I need to take that into account. So this is a negative acceleration. But all the time, our values of the velocity, so this is 0, and maybe this is 1 meter per second, and this would be 2 meters per second. Over here, it would be 0, and maybe that's 1 meter per second, and 2 meters per second. So just because the negative sign is over here doesn't mean that it's less than 0. That wouldn't make sense. You can't go slower than stopped. So the negative sign just indicates the direction. So if I'm moving to the left and I also have an acceleration to the left in negative directions, these two arrows, which we use to define vectors. Remember, scalars are quantities that just give you the amount. A vector is a quantity that gives you magnitude, the length, and the direction, so which way it's pointing. So these two vectors are in the same direction. I have both negative velocities combined with a negative acceleration. And so these two arrows are in the same direction, and that will cause, this acceleration will increase the length of that velocity vector for every second. Now, conversely, over here, we've got a positive velocity, and we have a positive acceleration for that first interval of time. So these two, velocity and acceleration, are in the same direction. So in both cases, when the arrows for velocity and acceleration are in the same direction, then we have a case where it is speeding up. So it's getting faster and faster. One is moving in the positive direction because it has a positive velocity. The other is moving in the negative direction because all of these velocities are negative. Let's take it a little further. So in this case, we have an object that's moving to the right because all of these velocities would be positive values. And so it's moving to the right because all of the velocity values are positive. And even though this line looks like it's going down, it's actually still just positive velocities. So at the mid, or the time here, I'll use a capital T for that time there. At that time, there's a change in the motion. So originally, the slope of the line from the beginning to capital T is a positive slope. So the acceleration is positive. Remember, the slope is the acceleration. And the velocity is positive. All these velocities are positive. Now, at this time, right here, there's an instantaneous change. So, for example, you are in a car and you speed up, and then immediately you have to hit your brakes because maybe the car in front of you stopped. So this section of line actually has a negative slope. So this would be a negative acceleration. But all of these velocities are still on the positive axis. So you're still going forward. So let's say that you are waiting to turn into the school parking lot and the car in front of you moves a little bit. And so you hit your gas and move a little bit, but then that car stops. So that you have to move your foot to the brake and slow down to stop. You didn't stop moving in the forward direction. The whole time you were speeding up and slowing down, you were moving in the same direction. So if we were to draw a dot diagram, the car starts from rest and slowly increases and then begins to decrease. So our dot diagram would look something like that, where we cover more distance each time interval, and then we start covering less distance in each time interval until we stop. So at this point, the velocity was 0, and at this point, the velocity was 0. So in this case, we have positive velocity still. Now that means we're slowing down. So remember, for the first part, for the first half of the time interval there, the velocity is positive and the acceleration is positive. So that would look like a positive velocity and a positive acceleration. Those two arrows are in the same direction, so that gives me speeding up. Now, the other side here, we go from a maximum velocity down to a 0 velocity. So we're slowing down. However, our velocities are still positive, so it would look like our vectors would look like a positive velocity, but with a negative acceleration. And those are opposite of each other, so that's going to indicate that it's slowing down. In this case, our object stopped. It started from rest, sped up, slowed down, and stopped, all the while moving to the right. So what would that look like on a position time graph? Well, remember, our position time graph looks curvy for our changing velocity. So in this case, let's see what our velocities tell us to graph. So I resketched the velocity time graph here. We had our speeding up and we have our slowing down. In the positive direction, we're still moving in the positive direction. Now this, remember, that velocity value tells me the answer to the question. What is the slope on my position time graph? So initially my slope is 0. And then later my slope goes to a very positive number. And then later my slope is returning to 0. And I moved it up here because all the while my object is still moving in the positive direction because these velocities are all positive. So we must always be moving in the positive direction. So connecting those shapes, I get that it speeds up and then it slows down. So that would be the speeding up part and then the slowing down part. So if I use capital T to be the special time that this changes and it's moving in the right direction the whole time and it's moving towards the right the whole time because the velocities are positive numbers, then these two match. Now let's look at another case. This one shows me that initially the velocity is positive and non-zero, because zero would be here, and these would be all of my negative velocities. The acceleration is the slope of the line, so the slope of the line from here to here, that whole thing is a negative slope because it's not a rise. The rise is negative, so we go down and over, down and over, down and over, and that gives us the negativeness of that slope. Now, initially, up here, before t, the particle is moving in the right direction, towards the right. So the velocities all up here are positive velocities. Now, those positive velocities are decreasing until they reach zero, where the object stops. And that's a really big deal. So the object is going to stops at that point right there because the velocity is zero there. Then later, after capital T, the particle continues to move, but all of these velocities are negative because it's below the time axis, so we have negative velocity. So if I use my vector argument that I used earlier for the top part, okay, I have a positive velocity and I have a negative acceleration. So this is my velocity vector and this would be my acceleration vector. And that tells me it's slowing down. That's my abbreviation. And that does make sense because it starts at a very positive velocity and it goes to a zero velocity. Now down here, we have a negative velocity, so I'm going to draw an arrow to the left to represent the negative velocities, and the acceleration is still negative because the slope of this whole line is negative even when the velocity is zero. So you have a negative acceleration. I'm going to draw that with an arrow to the left, A, and that gives me two arrows in the same direction. So it must be speeding up. That's my abbreviation for speeding up. So overall, I can describe the motion of this particle as having a positive initial velocity very fast, but it's slowing down as it's moving to the right until it stops. And then it turns around and moves in the opposite direction, the negative direction, and it's speeding up the whole time.